Okay, today we move to the chapter 5. The topic is the control volumes approach and the continuity equation. So in the following chapters for the chapter 5, 6, and 7 are associated with the physical property exchange along the fluid material boundary. So the chapter 5, the physical property, we are focusing on the mass, and the 6 we are talking about the momentums, and the chapter 7 are associated with the energies. So the slide showing here is the learning outcomes in this chapter 5. The first one, we are introduced the flow rate, and the flow rate about the mass and the volume flow rate. And we will introduce a little bit related to the mean velocities under different flow conditions. And then the secondary sub-chapters are related to the control volume approach, which we will apply the control volume approach to better understand the physical material properties exchange along the fluid boundaries. And one important ideas will be also introduced is the Reynolds transport theory. And we will introduce the main ideas about the continuity and solve the problem by using the continuity equations. And the final, we will go back to see the cavitation phenomena, and based on the ideas I teach in these chapters, and then we will be very helpful to us to better understand the cavitation phenomena. Okay, so what's the flow rate? And now the topic we are focused on the volumes. So this is the formula we are introduced for the volume flow rate. And usually we call that the discharge. And they use the Q. Okay. So as you can see, the discharge is defined by the volumes of the fluid and passing through a cross-section areas per interval of the time. Okay, so that's the important for the find out the discharge is the cross-section areas, and how many times your volumes, the fluid volumes just passing through the cross-section area. So as you can see the different cross-section area, and we can define the volume changed per unit time. Okay, the volume changed per unit time, and the different time intervals of the air, and how many volumes passing through, okay, along the mouth. Okay, so to understand the discharge, well, based on the different conditions. The first condition, we assume the flow is uniform flow. So let's indicate the velocity always the constant values. So in here we have the constant velocity, and the second, we need to find out where is our cross-section area. So as you can see, our cross-section area is the circle shape. Yes, the circle shape. And in that case, the normal factors of the cross-section area is always parallel to the flow directions. Okay, this is our flow directions. Okay, and then because we already know the interval, time interval is delta t. So we have the time interval. Okay, so and we know that the velocity v constant. So we know that the length, the passing throw length. So this is our length. Okay, so you have the length L, and you have the cross-section area of the A in here. So this is the volumes passing through with the delta T. So if you have the volumes changed and you have the delta T in here, so you can compute the and we can rewrite the volume to be, because we know that the L is the velocity multiplied the delta T is our L, and multiply the cross-section area is the total volume changed. So that's the AV delta T showing here. So you can see that the delta T will cancel out. And then finally, we know that the discharge is equal to the velocity multiply the cross-section areas. Okay, so this is the basic ideas, and you can check the dimensional of the discharge. The dimensional of the discharge will equal to the meter cubic per second, and you can check from the right hand side in here, because the velocity dimensional is the V meter per second, and the cross-section area dimensional is the meter square. Okay, so that indicates the based on the dimensional of the discharge is the per second meter cubic per second. Okay, and now we change the different flow conditions. Right now we assume the flow is a non-uniform flow. So because the flow is a non-uniform flow, so we need to use the sum of all cross-section area with the different velocity per dot. So the idea is we have the different cross-section area, so we have the different velocity, flow velocity, and the different cross-section area we have a different area size. So we just use the sum sigma sum all of the V multiply the dA, and then and then we can calculate the final discharge. And the idea is we also can use the integration operator to sum all of the small piece cross-section area with the different velocity functions. Okay, so that the idea is if your flow is a non-uniform flow, but in that case, the flow directions is also parallel to the normal factors of the cross-section area. Okay, so the flow flow velocity factors also parallel to the normal factors of the cross-section area, but the condition is changed from the uniform flow to non-uniform flow. So we need to use the integration operators to sum all of the discharge contributed by the small piece cross-section area. Okay, and then in that case, if your flow velocity directions is not parallel to the normal factor of the cross-section area, we need to use the dot per dot operator. So you need to apply dot per dot. That means you can see you have the velocity directions along this blue line, but you have the cross-section area is here. So in that case, the flow velocity direction is not parallel to the cross-section area normal factors. So we need to project to the normal factor directions. So as actually we know that the theta angle in here. So the V vectors dot with the cross-section areas and will equal to the V absolute multiply the cosine theta and the dA scalar. Okay, and the dA scalar. So also the absolute. So that means this is only for the small piece of the cross-section area. So finally, we would like to calculate the final discharge. In here, we need to apply the integration operator for all of the small cross-section area contributed to the discharge. Okay, so I can summarize the ideas. The first one, if we our flow condition is uniform flow, so we can directly apply Q is equal to the velocity and multiply the total cross-section area. And in that case, we assume the flow velocity direction is parallel to the normal factor of the cross-section areas. But if right now the same, but the flow changes to the non-uniform flow, and what's the difference? In that case, we need to use the integrations and integrate all of the discharge contributed to the small piece of the cross-section area. But right now, if not the flow velocity direction is not parallel to the normal factors of the cross-section areas, so we have the general formulas. The discharge will equal to also integration, but the velocity factors have the product with the small piece cross-section area factors. So this is only 3 formula to calculate the discharge under different conditions. Okay, and then the final one is more general formulas. The Q will equal to integrate of the velocity factors dot product with the small piece cross-section area factors. Okay, so and we move to the next topic. We are focused on the mass. So actually, we know that what is the mass flow rate. It indicates that we have the mass of the fluid and the passing through with the cross-section area per interval of the time. So only one difference for the unit, we know that we have the discharge in here, and the unit is the meter cubic per second, and we have the density in here. And we know that the dimensional of the density is the kilograms per meter cubic. So if the density multiply the discharge, the final dimensional will equal to the kilogram per seconds. So that we know that the dimensional of the mass flow rate in here is the kilograms per second. So the idea, how can we calculate the mass flow rate based on the discharge? So simply we just multiply the fluid densities with the discharge, and then we can convert the flow rate to the mass flow rate. Okay. So this is our final general formulas for the mass flow rate. The density in here multiply the velocity factors with the dot product and the small piece of the cross-section area factors, and we can calculate the mass flow rate. Okay, so what's the ideas for the mean velocity? So as a sentence showing here, we know that the mean velocity is an area weighted average velocity. So what the meanings? If you based on the equation showing here, you know that this is the velocity, and we have a piece of the cross-section area in here, and we apply the integration operators, and then finally divided the total areas of the A. So what are the area weighted? Because different velocity multiply the different small piece of the cross-section area. So in items for the dA, we call that the area weighted. Okay, the area weighted coefficients multiply the velocity terms and do the integrations. Finally, we divided the total areas. That's why the mean velocity, we can call that is the area weighted average velocity. So how can we use the mean velocity? Based on the equation shown here, you know that the discharge will equal to the mean velocity multiply the total cross-section area. So if we know that the true mean velocity under our flow conditions, so we can calculate the discharge very quickly. Okay, so the table summarizes some different environment will have a different relationship between the mean velocity and the maximum velocities. So how different conditions we have shown in the table. So the first one is a round pipe, and the round pipe flow, and the second is a rectangular channel flow, and the final also in a round pipe, but under the turbulent flow conditions. Okay, so in the right hand side of the table show the different formulas of the ratios between the mean velocity and the maximum velocity. For the round pipe nominal flow, the ratios between the mean velocity and the maximum velocity is equal to 0.5. And for the nominal flow, but in the rectangular channel flow, we have the ratios is 3/2. And for the turbulent flow in a round pipe, as we know that the turbulent flow, the ideas will lead the velocity profile to be the uniform flow. So in that case, you can see the ratio is higher than previous two cases, much closer to the ones. Okay, so but the table just summarizes the results. But how can we know and how can we prove the ratio velocity in showing here? So the key knowledge is we need to solve the problem by the integration operators. So based on the general formula Q, and we assume the flow velocity directions is always parallel to the normal factor of the cross-section area. And then so we know that the Q can be divided by the velocity multiplied the dA, and we can calculate discharge. So the key questions in here, how can we define the small piece of the cross-section area under different flow conditions? So if we look for the channel flow, rectangular channel flow, the dA is equal to the width multiply the width multiply the dy. Okay, this is for the channel flow. But for the pipe flow, the small piece of the cross-section area is the ring shape. So the ring shape of the cross-section area can be defined by the 2 pi r, and multiply dr. Actually, the 2 pi r is the radius, right? Is the radius. So the radius multiply the width. The width is dr. The ring width is dr. So the cross-section area of the ring shape is a 2 pi r multiplied dr. Okay, so the basic idea for we have the dA, and if we have the velocity functions for the different flow conditions, so we can do the integration calculations to find out the final discharge. Okay, and if we find out the discharge, and we know that the discharge is equal to the discharge can be rewritten to equal to the mean velocity multiplied the total area, right? So we can define the mean velocity by the discharge divided by the total cross-section area. Okay, so the next slide we would like to discuss how can we calculate the ratios between the V velocity, mean velocity, and the V maxima. And based on this is the conditions is the channel flow condition. So we know that the ratio is equal to the 3/2. So how can we prove this relationship between the V mean velocity and the V maxima? So we go back to see the general formula discharge is equal to the integrations, and right now we have the V velocity is Vy for the channel flow, and the dA, we know that the dA is the width multiply the small changes along the y direction is dy, and the integration interval is start from the 0 to the water depth is the h. Okay, so we put the velocity function inside. So in here we have the V maxima multiply the h2y and the h squared over the y squared and the w and multiply dy. And then we just move the constant value outside the integration operators. So the V maxima is the constant values, and the channel width also the constant values. So inside we only have the h2y and minus the h squared y squared and the dy. So right now we can do the integration problems for our velocity functions. So this will equal to the h over y squared and the minus the h squared, but y cubed, and have the 3/1 constant. Okay, and the integration interval is start from the 0 depth to the h water depth. So we put the number inside. So we have the V maxima and the W, and put the 0 inside. So total is 0, and the h put inside. So we have the h squared divided the h minus the 3/1 h squared over h cubed. So we can reorganize the equations in here. So this is equal to the h minus 3/1 h. Okay, so finally we have the 3/2 h multiply the V maxima and multiply the width. So this is our discharge, and as I mentioned on the previous slide, the V mean velocity is equal to the total discharge divided the total cross-section area. And we know that the total cross-section area is the width multiplied total water depth, H. Okay, so that's Q, we have the 3/2 H V maxima W divided the WH over 1. So we can cancel out the HW and the HW. So finally, what we have is the 3/2 V maxima. So we can prove the relationship between the V mean velocities and the maximum velocity is the ratios of the 3/2. Okay, so this is only based on the different flow conditions. We have a different relationship between the mean velocity and the V maxima. So in the next class, we will also introduce the ratios between two velocities, but under the nominal flow in a round pipe. Okay, in a round pipe. Okay, so today we just stop here, and then I will introduce the quiz